equilibrium will prevent the universe from reaching this point out here. And the argument goes like this. At high temperatures, scalar fields, the scalar field action gets a thermal correction. And that thermal correction produces an additional term in our equation which goes like T squared phi squared. And what does that do? That adds to our potential, a harmonic potential, a phi squared potential, okay, which is going to work against the behavior, the unstable behavior, and keep the universe stabilized, and keep it stabilized in this region near phi equals 0.
Wait, where is this T squared phi squared coming from again?
Thermal corrections to effective potential. So I'm jumping ahead a little bit in stuff we're going to talk about, but I just wanted to relate to the story, to the current story about electroweak physics. It's this term, for example, which could stabilize the universe near phi equals 0, tends to stabilize the universe near phi equals 0, and then as the temperature drops, it would gently deposit the universe in this point over here. That's one of the arguments for why this may not be a problem for the future of for the past of the universe. How the universe got to be where it is. How to get to be in this place over here. And the problem with that argument is that the calculation we just did, that the electroweak interactions are not in thermal equilibrium coming out of the Big Bang. They don't come into thermal equilibrium until the universe reaches around 10 to the 15th GeV. Beginning at the Planck density, what you'd expect for the field to be doing is to be, well, varying rapidly over space and varying rapidly over time, over a region when you're at the Planck temperature, which is of order the Planck length or Planck mass in field. So the field has units of mass. So if the typical temperature is of order the Planck mass, the field should be varying by such a huge amount. But that leads to a puzzle. It's not in thermal equilibrium. If it's really just these potentials that are relevant in a field that's at first has very wildly like this, how does it manage to get caught into this little region over here? So just to give you an example, an analogy, imagine you go to the top of Mount Everest, okay, and you dip your little pinky finger into the surface, make a little dimple, okay, with your pinky finger. Then you ride over with an airplane, okay, and you drop a BB. Okay. Think about what are the chances of ending up in that little dimple. And work out the numbers. Beginning at the Planck density and ending up here is much, much less than that probability. So there's a puzzle. How is it, if this story is correct, that we end up over here? Now, as I said and as Nick emphasized, we did make various assumptions along the way. Assumptions about cosmology, assumptions about particle physics. Maybe there are new particles that appear at energies between 10 to the 11th GeV, where this thing is supposed to have turned over, and are present, and the scales we presently measure, which are on the order of TeV scales, or 1,000 GeV scales. Yeah, maybe so. That's in fact what we were anticipating at LHC, but we didn't see them. Okay? But there's still a big gap there. And it's still conceivable that there are particles there. But just finding new particles by itself isn't enough to do the trick. They have to be particles of the right type that would reverse the trend of the lambda. So just waving your hands and saying, I think there's some new particles, yeah, you can speculate that, and that's reasonable to speculate, but you actually know something more. They have to be particles which interact with the Higgs in such a way as to work in the right direction. So some people would argue that's an argument for supersymmetry. The supersymmetry is a possible symmetry which could protect this field which reaches the right segment of particles that can protect the Higgs from becoming unstable. But we don't know that supersymmetry is correct. That's a speculation. So one possibility is, there is new physics like new particles. The other possibility is this is really the way it is cosmologically, which means that's a big problem for the Big Bang picture. It means you don't want to end up starting in this state. This is what the Big Bang should be looking like. You have to be starting off in a more special state. And you better not get to really high temperatures, because thermal fluctuations alone, when they get to be bigger than 10 to the 11 GeV, if you think about a field like a particle, being shifted around by large energies, will tend to kick it out. Okay? Or tend to prevent it from getting there in the first place, is really what we mean. Will tend to prevent it from getting there in the first place. So, the other possibility is it's telling us something about the beginning of the universe, the Big Bang idea. The problem for the standard Big Bang idea, we have to imagine a universe which never gets too hot. That's pretty dramatic, too. So, this little story of the Higgs, okay, turns out to be, and measuring the mass of the Higgs, discovering the Higgs, and the way we happen to find it in our mass diagram, turns out to be much more interesting than simply, at least to my taste, than simply the verification of an idea that was developed in the 1960s. Because where it turned out to be in this mass diagram is in such a peculiar, unexpected place. Okay. Any other questions? I'll leave you to ponder the future of the universe.
So the Lambda turning back up asymptotically to infinity would explain this a lot better, because then it could have rolled into this stuff originally.
Yeah, so if there were, yes, exactly. Then that was the picture that everyone imagined up until recently, up until the LHC. So everyone assumed that was what the story would be. Or they assumed it would be in the unstable regime, and that they would also discover supersymmetry, and that would also be a nice story. So all the stories we anticipated, like most of the things that have been happening in physics in the last few decades, most of the things that theory has strongly pointed us to have turned out to be wrong, and this is an example of one of them. And so it points to new possibilities, dramatic possibilities, not small ones. Yes?
So what's like the next step in determining where we are on the stability chart?
Well, the first thing to do, that people will do, is extend the LHC to somewhat higher energies. That won't take us very far in energy, and even the next colliders that people are talking about won't take us that far in energy. You may be lucky, you may bump into supersymmetry. It's unlikely, or new particles. It's unlikely because even before you reach the critical energies where those particles would appear, there should already be indications turning on even at lower energies that would tell you they were there. They would hint that they were there through various interactions. So, for example, although a big deal has been made of the fact that LHC didn't discover supersymmetry, there were already a slew of earlier experiments which had already seen indicators of some new particles appearing that were always giving null results. So there was always kind of reasons why you should, there was a kind of precursor experiments. So we're kind of now in the precursor. So far there's no sign of any deviation from the standard model. As long as that's true, that means you have to go to substantially high energies to see such a thing. Okay. So all I'm saying is something's got to change. Something's got to be very different than what we expected prior to the LHC due to the Higgs. New particles, dramatically different cosmology, dramatically different future to the universe. Just one last comment before we all go. This is just one example of an argument that says that the present universe may not be in a stable configuration. I should also point out that almost any attempt to unify gravity with the other interactions, string theory included, suggests that we live in a metastable phase and not a stable phase. So there'll be some version of this same puzzle about how you got into that phase rather than a phase of lower energy. Okay, I'll stop there. Yes. So I didn't have a chance to get back to
That's okay.
Yeah. And I'm leaving in it. I'm not sure I'll be able to do it before spring break.
Okay,
Yeah.
no problem.
Okay. I'm not sure if I can be that helpful to you either, but that we'll find out.
I think
I'm happy to meet with you.
I'd love to hear your take on it, or I think you might be able to point to some interesting directions, or immediately to say, well, that's wrong for this and that.
More likely first, but not even that. We'll see. I'm happy to meet with you. So make it after spring break sometime. Is that okay?
Okay, thank you.
Okay.
I was just hoping to clarify the concept due date, because here it says 15th, and then on the PDF it says 13th.
That's what I mean.
Okay, so it's the 13th.
Yes.
Okay.
I just wanted to make sure the homework is on Wednesday.
Okay, the homework should be handed in on Wednesday. Because of my typo, it's okay if you also hand it in on Friday.
Okay.
It was my mistake.